For decades, the automotive industry defined safety through a physical lens, governed by the ISO 26262 standard. A vehicle was considered safe if wires didn't short-circuit, sensors didn't crack, and brake pads gripped rotors exactly as designed. But autonomous driving creates a new problem. We have to account for the moments when the hardware performs flawlessly, but the artificial intelligence steering the car misinterprets reality. The brakes work, but the AI ignores them because it categorizes a crossing pedestrian as a harmless shadow. To manage this specific danger, engineers rely on ISO 21448, or SOTIF, the safety of the intended functionality. SOTIF focuses on the risks that emerge when a system does exactly what it was programmed to do, but makes a fatal error due to the limitations of its own logic and perception. This forces a change in how we view a vehicle's release date. In the lab, a car's safety argument is tested within a controlled environment called an operational design domain. Once that vehicle hits public roads, the safety guarantees built in that lab begin to age immediately. For self-driving cars, the assembly line marks the start of a new engineering phase, where a static design is finally exposed to the mercy of an infinitely complex world. The real world refuses to stay static. Over time, the environment actively degrades the initial assumptions engineers made during development, a process known as context evolution. Cities might install experimental traffic lights that the car's vision models have never encountered, or climate shifts could trigger a freak blizzard in a normally temperate city, instantly blinding the vehicle's sensors and erasing lane markings. Human behavior shifts as well. As pedestrians get used to autonomous vehicles, they adapt. People learn that these machines are programmed to avoid collisions at all costs, and some begin deliberately stepping into traffic to force the car into an emergency stop. Together, these shifting variables create open-world problems. The variables on a live road are so chaotic and interconnected that a static algorithm written years ago can never completely account for them. When an autonomous system makes a critical error in the field, the failure rarely stems from a broken part. It happens because the specific version of the world the machine was designed to navigate has ceased to exist. To survive this shifting ground, Level 3 and Level 4 autonomous vehicles must possess advanced onboard monitoring to continuously watch their own performance. Clause 13 of the SOTIF standard requires these cars to carry two specialized diagnostic tools. These function as dual black boxes, each serving a distinct investigative purpose. The Event Data Recorder tracks crash physics, speed, braking pressure, and airbag deployment. The DSSAD records the AI's thought process, logging recognized boundaries, mode shifts, and takeover requests. While EDR explains destruction, DSSAD captures near misses, revealing moments the AI recognized confusion and avoided a crash. Measuring the wreckage of an accident only explains how a machine failed. Capturing the machine's moments of doubt provides the intelligence needed to prevent the disaster before it happens. Every time the vehicle encounters confusion, that DSSAD data streams back to the manufacturer through the SOTIF issue evaluation process, exposing blind spots the lab never anticipated. When engineers map this risk, they look at Area 3, the zone of unknown hazardous scenarios. This represents the dangerous, undefined territory the vehicle has just encountered out in the wild, sitting just outside the safe zone of known scenarios, which we call Area 2. The immediate defense against a new Area 3 threat is an over-the-air software update. Engineers can instantly restrict the vehicle's features or limit where it can drive, effectively fencing off the risk while a permanent fix is developed. Eventually, engineering teams redesign the AI's core logic so it can comprehend the new scenario. The threat is absorbed into the managed, structured realm of Area 2, moving it from the unknown into the known. This cycle of ingesting field data and updating the logic is what systematically shrinks the unknown into a calculated, manageable reality. This data acts as an active immune system, transforming a vulnerable machine into an adaptive network that learns from every mile. This is the philosophy of ISO 21448 Clause 13. An autonomous vehicle safety argument is a living document that must be continuously proven for as long as the car is on the road. Ownership of an autonomous vehicle involves a lifelong data-sharing agreement, placing the consumer inside an engineering cycle that continues for the life of the car. Because the stakes are so high, manufacturers are encouraged to contribute to a shared body of knowledge. By sharing near failures across the entire industry, global safety standards can rise before those edge cases turn into tragedies. True trust in autonomous driving relies on the machine's relentless capacity to learn from the unknown, ensuring the vehicle is safer today than the day it left the factory.